Hush, too much talking. Everyone has notes now? Leave, yep, did you get notes? Sweet. This is what I discover, and I know this every year with quadratic formula. Y'all can't do arithmetic. I would bet you the grades on this quiz would have been higher if you completed a square on every problem. And I'm saying that sarcastically, but there's a lot of truth to it. Oops. I gave you the wrong notes.
No, give us the right.
No, I gave you.
Does that mean that every problem could have been
Are the tests, are the quizzes in?
Quizzes will be in fourth period.
It's today.
So the end of next period.
Oh, Mr.
So it's frustrating when things I saw that were frustrating. A lot of people don't realize when you take the square root of both sides, you have plus or minus. You have two roots. So that was an error I saw a lot. Anytime someone solved with a quadratic formula, I'd say at least a third of the class missed that problem. Not because your algebra was wrong, but negative 4AC goofs you up when you have negative 4 times negative 2 times negative 3. You're like, oh, there's all these negatives. I think it's positive. No, it's negative. So just a few things to think about when you're doing that. And, you know, I know that some people say, well, if we could use our bigger calculator, we could do it. I agree with you. But honestly, a lot of times, completing the square is not a hard concept. And it was always the same concept all the way through. So I think I might start venturing to say, you know what, I'm not even going to show the quadratic formula because arithmetic sucks. And but anyhow, we're going to start projectile motion today. And this all has to do with, you know, the application of quadratics in the real world. Now, I want to give you some ideas of things that you will see quadratics used as. Quadratics are used in braking distance. So the brakes on your car or on your bike or motorcycle is modeled by a quadratic function. Okay? That's actually there is a formula that is used that if you get into a car accident, there's things that they can see based on, you know, hi, it was posted as 30 miles an hour in the school zone, and I realize you have skid marks of 115 feet in length. Yeah, I was doing the speed limit. No, you weren't. And they can find that out pretty easily by looking at the path of destruction of your car as well as where your initial skid marks are. And you're like, well, there's no skid marks because I have anti-lock brakes. There is an initial skid that happens as soon as you hit your brakes. Your first reaction, if you're going to collide with something, is to hit your brakes as hard as you can. So ABS brakes actually have a skid mark about this long. It goes, and then it goes to slow you down. But it's a quadratic function that they could do. Okay, that was your initial impact of your brakes. Here's how far you went. You were actually doing 71 miles an hour. And so that's just one application of it. But a lot of times we talk about the objects that are thrown to deal with the parabola. So if you kick a soccer ball, kick a football, throw a soccer ball, football, baseball, anything like that, that goes in some parabolic arc. So it gets to a maximum height, and then it comes back down. So those are a few things. So they talk about this. They say the path, the path thrown or filed of a projectile on Earth is a parabola. Okay, it's actually a parabola everywhere. It's just we're going to use an equation that's exclusive to Earth. It would be different on other planets because of gravitational pull. As soon as a projectile is released, the force of gravity causes it to accelerate to the ground. Okay, so you all might have heard this idea, and it's hard to fathom this, but if you were to take any type of gun and you had it parallel to the ground and you were to shoot it, and at the same time you would release a bullet out of your hand from the same level where that bullet was going through that barrel, the bullet that you dropped and the bullet that you shot will hit the ground at the same time. Sorry if I'm interrupting you. Yeah.
Wait, how?
Because the only force acting upon the bullet as it leaves the gun in the vertical direction is gravity. So it's really hard to fathom if you shoot a bullet out of a gun that's perpendicular to the ground, and at the same time you drop that bullet. Yes, this bullet lands at your foot. This bullet travels 1,500 miles away or 1,500 feet away and then hits the ground. It's just as accelerating at that time. It's kind of a strange thing to fathom that would really take place because it's like there's more to it. There's a lot of great stuff with physics that this all works with. But since the path is a parabola, the maximum height of the projectile will occur at the vertex. So if I throw a ball in the air, it's going to go up. It's going to get to a maximum height called the vertex, and then it's going to head on its way down. And we can use these equations. But then they have all these different things that they start using in there. They use H naught, which is an initial height. They use V naught, which is an initial velocity. They use H at t, which is the height in respect to time. They use time. You have all these variables that do occur in here. And then they give you an equation that is H at t is equal to 1/2 gt squared plus V naught t plus h. And you're like, what? Don't worry, they're all pretty simple when you start recognizing what they come from. So this right here is the initial height. Okay, if you threw a ball into the air, my initial height is the top of where my hand is to the ground. That's the initial height. So I don't know, 6'5", 6'6". V naught is the initial velocity. It comes out at 35 meters per second or whatever. Okay? G is gravity. And usually we don't recognize gravity here as negative 9.8 meters per second squared because we're Americans. We don't use meters per second. We might often use it as negative 22 feet per second squared. And that's the acceleration due to gravity, and that's just the conversion from meters to feet. 1/2 is constant, and then you have t squared and t. And t squared and t, one's the quadratic term, which is the squared term. One's the linear term, which is the t term. And then the h naught is a constant. Okay? And again, with gravity here, they have negative 32 feet per second. Oh, I misspoke. I said negative 22 feet per second. I'm sorry. I was going off the cuff and I dropped the value. Okay? But all of this will start making sense. The nice thing is all of these problems use the exact same thing. Your initial velocities, if you throw something upwards, it's a positive initial velocity. If your initial velocity is directly horizontal, then your velocity is 0 because you're talking about a vertical component. And if you were like standing on top of a building and you saw your friend walking and you had like a water balloon, you want to throw it at him, being you're throwing it towards the ground, your initial velocity is actually negative, or positive, excuse me. All right, let's play with this equation a little bit. Okay, everyone agrees this is a big equation. Anyone like, dude? So nice thing is this is going to be the same equation we're going to use. We simplify it to this. Yes, it's a nice thing that science and math all work together. Okay, so all they did for the one that I highlighted in purple is I plugged in 32 feet per second squared, and for g, which is acceleration of gravity, which then you go negative 1/2 times 32, and you come up with negative 16. Is that okay?
Yeah.
So that purple equation is basically what we're going to start focusing on. And there's a lot here that we start dealing with on this problem. It is written that the height is a function of time, height after t seconds. So does everyone agree if you throw something into the air, it's going to go up? It's going to be in the air for a certain amount of time, and then it's going to come back down. Yes. Mm-hmm. Now, I know some people have some big arms out there, but I hate to tell you this, everything you throw upwards will come down. Some of you will throw it further and higher than others, but for the most part. Okay, so height after t seconds. V naught, which is that V little sub zero, that says V naught. That's the initial velocity. And usually they'll give you the initial velocity as part of the question. You plug that in. Watch your signs, please. Okay? T is time in seconds usually. You could make it time in hours. You could make it time in minutes. Look what your question is asking. So it doesn't have to be necessarily time in seconds. But if we're using negative 16t squared, you're talking about feet per second. So you might have to use a little dimensional analysis, which if you don't know what that is, I can show you. We will have it throughout the class. It actually will save you in science classes later in school. And then h naught's initial height. So if it starts from the ground, the initial height is 0. It starts on top of a building. The initial height is the height of the building. And if you were to start like underground, if let's say you're standing in a pit and you decided to throw something upward, your initial height is negative. Okay? So everyone kind of following what we're doing. Can everyone see why this is a quadratic? What stands out up there to make it quadratic? It's squared. That's the only thing that makes it a quadratic. Okay? If you have a graphing calculator, grab one. If you need to get one, grab one from back there. Please. We ready? So I don't think there's too many more slides, but we're just going to kind of go with these, and these take a little while to do sometimes. Okay, projectile motion questions refer to the object that is thrown or dropped and then proceeds with no additional forces on it. Okay, so the big questions when you start talking about physics, especially goes with when you fire a bullet out of a gun and you drop the bullet from the same height as that gun's being fired, they both hit the ground at the same time. Some people say, yeah, but you have wind resistance acting upon the bullet itself. And the wind resistance is the horizontal force on it. Okay, you have multidimensional forces that act upon things, but when you talk about gravity, the gravity is the force towards the earth. It's pulling it back down to earth. It's negative because you're being pulled towards it. If you go away from it, it's positive. Okay? In order for an airplane to lift off the ground, the airplane itself has to create something called lift with the wings. Does anyone know how lift works?
Like the
Lift of an airplane?
Oh.
Like the app, yeah.
No, not the app. Like when you're in an airplane and you accelerate up to about 165 miles per hour, how does lift work?
It pushes the wings in.
How does the wind?
Yeah.
Yes.
Air goes under the wing and pushes it up.
Okay. Go ahead.
Like pressure.
Pressure. Okay. It's something called Bernoulli's Principle. Okay, Bernoulli's Principle, I'll explain it a little bit more in detail with the airplane wing after I tell you this. If two trains are coming towards each other, they have to slow down because of Bernoulli's Principle. The reason is as they pass each other, you create a negative pressure in between the two trains. And if they're going fast enough, the two trains would start leaning into each other. And if they're going really fast, they would actually collide with each other because they would lean over on the tracks because the air pressure between them is less, so they are drawn to a lesser pressure. Okay? That's exactly how an airplane wing works, like a train. You're like, trains and airplanes are different. I understand, but Bernoulli's Principle isn't. So when you are in an airplane, they have something called flaps. And the flaps of the airplane actually create a larger surface area on the top of the wing while creating a smaller surface area underneath the wing. So what you want is you want the air that is going over the top of the wing to create less pressure than the air underneath the wing. And by you doing that, you create lift of your wing. The ideal speed for an airplane to take off is about 165 miles per hour. Okay? But here's where it gets tricky. Is that airplane on that runway getting up to 165 miles per hour?
No.
Sometimes. Not all the time. You want the air going over the top of the wing to be doing 165 miles per hour. So does anyone know why we have airport landing strips that are going all different directions? It's not because of the wind blowing against it. You want to land, an airplane can land in really high wind situations, which it sucks when you're a passenger because you're bouncing around. You want to have your airplane face the direction that the wind is coming. So you want the air blowing into the face of the airplane. If you do that, the airplane doesn't have to accelerate as quickly because it already has airflow going over the top of the wings, and you only want that airflow to reach 165. The airplane itself doesn't.
That's pretty good.
Yeah, it's called physics. It's pretty amazing how it works. But that is a huge thing. Now, give you a story about physics that was real life. I grew up. Hang on, I gotta get this. I'll be right back. You'll like this. I'm a dork, y'all knew that.
I guess that fits it out. Physics? Physics?
When I was a kid, my dad had a hot air balloon. And this science folder here, this is from a long time ago. This hot air balloon right here, that's my dad's hot air balloon.
No way.
This was when we were in Fountain Hills, and there's actually quite a few hot air balloons that are on here. This is Jim Kearns, Judy Holtz. My dad's, I don't remember who this was. This is Jeff Woodhouse's hot air balloon. So this was at Fountain Hills in Arizona at a hot air balloon event. If you look really hard at this picture, nope, Woodhouse's balloon is in the way. I would have been either in the basket or holding the basket down while someone else got to climb in and go fly. Neat. Hot air balloons are pretty cool, but hot air balloons also obey laws of physics. And you don't want to fly a hot air balloon when it's windy, because it's easy to take off in a hot air balloon when it's windy. But guess what? When you land, you bounce and drag and bounce and drag and bounce and drag until you get enough cool air in the balloon itself by using the parachute top at the top to vent it to allow your fabric of your envelope, which is the balloon, to lay over and deflate. But there's something dangerous that happens, and I remember when I was a kid, this was in 1982. We had just gotten our hot air balloon. We were at Albuquerque Balloon Fiesta in Albuquerque, New Mexico, which is the largest balloon fiesta every year. It's actually right around now it'll happen. It's, Oh, it was last week? Okay. It's a pretty cool event, but the problem is you have anywhere from 800 to 1,000 different hot air balloons that show up to this event. What happens when you have 800 to 1,000 hot air balloons? You have people who aren't as bright as other people who are deciding, I'm going to have this thing that fills up at least 77,000 cubic feet, and we're going to launch into the air. Okay? So a lot of times they have rules. They'll tell you if you're taking off out of the field with all the other balloons, and they usually call that a mass ascension, you cannot bring your hot air balloon, you cannot allow it to rise or descend, so ascend or descend, more than 500 feet per minute. The reason is, when you're in a hot air balloon, you can't see above you. You can see below you, but when you look up, you have these pretty colors of the hot air balloon above you. If there's another hot air balloon above you, you can't see it. Guess what the guy below you sees? He sees you coming up. And I remember one time, without even thinking twice about it, we were taking off out of the field, and we're up about 700-800 feet, and this guy comes like a bat out of hell. He's coming straight up at us. You can't steer a hot air balloon. You can't say, oh, let's go that way. The wind's going that way, guess which way you go? You go that way. Okay? So, I am in, I mean, it's unbelievable when you're flying with this many hot air balloons in the air, but I see this guy, and my dad's flying at the time. I see this guy coming up. I'm like, Dad, this guy is coming up on us quickly. Well, we can throw both burners on, and it's going to take about 25 seconds for the hot air to react to the buoyancy to allow the balloon to ascend higher. But here's the problem. Who's above us? I don't know. Maybe another hot air balloon. But guess what the basket of a hot air balloon will do to the ripstop nylon of the fabric of the hot air balloon? It'll rip it. You put a big hole the size of, oh, I don't know, this whiteboard here in the top of a hot air balloon. It doesn't go like that, but it's going to go, and it's going to lose all its hot air, and it's going to sit there, and it's going to descend, and it's going to descend quick.
Basket catch on fire?
No, because it's just hot air. So the hot air, it's not a hot enough connection to a louder thing. So a few things about that. That's a great point. The maximum heat at the top of a hot air balloon can't get above 300 degrees. If it does, the ripstop nylon melts. That's a bad thing to happen too.
Does it take a while to get them up and going?
So if you were to go quickly, you could probably go from where you're drawn out and all the cables are thing to using your inflator fan, which is the same thing the fire department uses to evacuate the smoke out of a house. Probably 7 minutes. So it's not a horrible amount of time. The burners themselves, we had 2 Mark IV burners that produced 36,000 BTUs when you had them both kicked on, so you could kick a lot of heat up quickly. So anyhow, we have to do this. What's your main goal if an emergency situation is going to take place? If you are the one who's involved. Yeah, you want to survive, right?
Yeah.
So Dad, who's the pilot, doesn't want to put us in danger to have our balloon go upward and eventually have another balloon rip through the top of us. So I do this. My dad's got me by the back of my jeans. I lean over the side of this basket at 800 feet up, and I am pushing down on this guy's hot air balloon that is coming up onto us so our basket doesn't rip it. Now, if Dad lets go, Sonny Boy's gone. Okay?
What did your jeans for?
Huh?
What did you lose pants?
They were Levi's, they weren't coming off.
I wasn't a sagging guy. I always wore Levi's. So, I just remember that day. I mean, 1982, I was 11 years old. Like, hey, this sounds like good. Dad, hold my pants. Okay. And I'm over the side, my feet are kicked up, and I'm pushing down on this guy's balloon so we didn't rip through it. Fortunately, we didn't rip through it. But kind of a scary, tense thing. Now, what was really kind of fun, and I never did this, but I saw people doing it, and I thought they're sitting on something that's hot. I said the top of the balloon shouldn't go above 300 degrees because the fabric melts. People used to sit on top of the hot air balloons. They'd harness themselves in on the very top rope, and they'd be sitting on top of these big pillows, the hot air balloon, and they'd be flying. Yeah.
That's so cool. Did you ever do it?
Oh yeah, we had an event where we took a whole bunch of Navy SEALs up in different hot air balloons, and so we weren't sure what the hot air balloon would react like when you drop 180 to 200 pound person out of it at 6,000 feet. You didn't know. So things what we would do, and I have an old VHS tape. I don't know if you know what that is. It's these tapes about this big. I have this camera you put on your shoulder.
Yeah.
We didn't have cameras like this going, hey, I'm going to do this. Okay? This was huge. It was like the size of that computer. Rested on your shoulder. You had a little hand piece, little eyepiece. I have this video where I am holding on to one of the ropes inside the balloon because I don't know how the balloon is going to react. This guy who's a Navy SEAL gets up onto the edge of our hot air balloon. We actually took the balloon up to 11,500 feet. We were against FAA regulations because 10,000 is where you have to have oxygen. You're like, how'd you survive at that? If you skied any of our ski resorts, you've been above that. So FAA just kind of goes panicky if you go above 10,000 because you don't have enough oxygen. Whatever. So we're up there, and you know it's weird is when you're a kid and you hear that and you're like, oh, the air's too thin up there. It's like, am I going to pass out? No. But it's the safety things they have in place. Well, we're way up there, and we're up that high. You're standing in a basket that is a wicker basket. Your parents might have wicker baskets that you have blankets on sitting on the fireplace at home. Okay, same thing. That's all we're standing in. So between me and the ground is wicker. We have 4 tanks of propane, 10 gallons each, so we have 40 gallons. They're in each corner of our rectangular basket. We have 2 burners above us. We have uprights that are holding the burners above us so the burners don't crash down on our head. You don't want something that's hot and fall on your head.
You don't?
Anyhow, this guy gets up on the side. There he goes. All right, so we start. We have a descent of about 300 to 400 feet per minute on a descent. It's not a fast descent. You're not going, you're descending. He goes, all right, see you guys later. He goes, does a backflip out of the balloon. And I got the video of it. I was like, dude, this is so cool. And he was like, there he is. And then you look over the side, and you jump out of an object, and you don't release your parachute right away. You become a dot real quick. It's like, he's gone. So it was pretty cool. But anyhow, there's your hot air balloon story about Bernoulli's principle. All right.
Thank you.
How do you control a hot air balloon? Like, how do you know when
There's a hot air
Yeah,
balloon.
you
the
can.
wind?
Steering wheel.
Isn't there like
Is there a steering wheel?
you pull the
How do you
and pull
higher
certain
you just
parts of
wait
the
out 8 miles an hour when you're left.
balloon down so like air gets
Otherwise
in
you
and then
can't
you
fly.
turn. I went higher balloon over
Because then
Colorado.
it's
All right. So no, you don't have a steering wheel. You can go up and down. You can control it with the vent at the top and the burners. The more heat you put in, the higher you rise. The less heat, the more you descend.
So don't go side to side though.
It doesn't go side to side, back and forth.
Isn't it the expensive?
Well, you are the wind. So the weird thing about in a hot air balloon, you could be in 30-mile-an-hour winds and you don't feel any wind because you're going as fast as the wind. Everyone else's hair's going sideways down on the ground going, wow, it's really windy. And you're like, it's windy down there?
You're gonna end up like.
Oh, yeah, you travel far. All right. Let's play with this. All right. Projectile motion. Projectile motion, quadratic function. How long does an object take to reach the maximum height? Okay, so x equals t. T is equal to negative b over 2a. Negative b over 2a finds us the x component of the vertex. You then plug that in to find the y component of it, and you find the vertex. Or you use that calculator, and you find a max. All right. I'm going to get to a problem. We're going to work it. Okay. So it says a cliff diver in Acapulco, Mexico. Ooh, let's go back to Acapulco. Jumps off a cliff into the ocean below. His height is in meters from the water. T, seconds after he jumps in, is given by this equation. Okay, so they're giving us a little bit different equation, but this is our equation. How should we label the x and y axis on the graph? And what about the x axis and the y axis? Okay, how should we choose our window? Okay, so first thing, let's plug this equation in to our calculator. So we're going to go into y equals, turn it on first, y equals, go to zoom standard, and hit zoom number 6. So here, I'll walk through it. I'll go here. I'm going to say, hey, got my calculator on. I'm going to go to zoom. Gotta get out of that. Sorry about that. So I gotta go here, get rid of that, delete that, zoom, and then I'm gonna go to zoom standard, and I'm gonna get rid of that cool stuff. I'm gonna go to y equals, hit clear. Okay. So what was the equation? I'm sorry, I forgot it. Negative 4.9. So you use this negative. 4.9, excuse me. It's t squared. We know to use x squared, right, Cooper? Plus 1.5 x plus 17. Okay, well, I went to zoom standard, which was zoom 6. And if you do that, if you go to zoom 6, you might see that. Do I see the whole parabola?
Nah.
No. There's part of this parabola I'm not worried about. Okay? This here is time in seconds. So the x-axis is time in seconds. And this is feet, or this is height in meters. Okay? Am I going to jump off a cliff and have negative seconds?
No.
No. Am I going to jump off the cliff and am I going to go into the ground? Well, I hope not.
No.
I hope to break the surface of the water, go underwater, but as soon as I hit the water, it's basically ground level. Okay, so what I can do with my calculator is this. I'm going to change my window. I hit the window key, which is right next to y equals, right, Cooper?
Yes, sir.
I don't want to worry about negative numbers, so I'm going to make my x minimum that. I'm not too worried about negative numbers in the y direction. I might have a little bit. It might make it like -2. And I realized my vertex was off my screen, so maybe I put that to be 30. Okay, I might have to adjust it a little bit more. I'm just trying to take some guesses, but I've changed my window to deal with just positive time in the x direction. I went a little bit on the negative for the ground level for a reason, and I'll show you that right now. So if I hit graph, that's basically the guy jumping off the cliff, and then it looks like in about 2 seconds, he's going to hit the water. Okay? So he jumped from this height, and he got to right here. Now, how do we figure out the vertex? Well, I'm going to go back into the window, and I'm going to go just a little tiny bit in the x direction being negative. So I went to -3 there. If I hit graph, that shows me my parabola. Can I see my vertex, my highest point on my screen?
Yes.
I can. Okay, so what I'm going to do is I'm going to do this. I want to find a maximum value. This is the coolest steps ever, and it's recorded. So if you don't see it right away, please, by all means, go back and figure it out. It's like at 31 minutes into the video. Okay? So I want to do this. I want to go second. You still with me? I hit trace now, and it gets me there. I want to find the maximum, so I'm probably going to hit what?
Minimum.
Number 4 to get a maximum, right? So you can either go down to it. Now it says left bound, so you're going to use your arrows to get to the left side. Nope, I got to come back this way. Negative, negative, negative. Okay, I got to get to the left side of it. See how my cursor's coming up? Am I on the left side of the highest part? Hit enter, then move it over to the right side. So in between these two, you're going to have things. It says, hey, do you want to guess? No, I don't want to guess. Hit enter one more time. So at 0.15 of a second, this person got to their highest part, which was 17.1 meters. Now let me ask you this. This person leapt off of a cliff. If they stepped like this, my vertex would be at 0,17. But at 0.15 of a second, he didn't step off it, or she didn't step off it. He actually went jump. Make sense? So this tells me at 0.15 of a second after this person jumped off of this cliff to go into this water, he got to 17.11 meters above the ground. This x-intercept means nothing because he didn't go negative seconds. This means something. This appears to be 2. Is it exactly 2? I don't know. Let's figure out what it is. So I'm going to hit second. Still with me? Trace. Still with me? And what's it called when it crosses the x-axis? Intersect is if I have two equations together.
0.
0. Good. So it's called a 0. Okay, so I'm going to hit the 0, and it's going to say, hey, left bound. Does it look like I'm probably on the left side of where that 0 would be?
Yeah.
Okay, you hit enter, and then you want to go on the right side of it. And you want to make sure that your y component is a negative number now. You want to make sure there's a sign shift. Hit enter one more time. Hit enter one last time. So at 2.02 seconds after this person decided to jump, they landed into the water. How long is a 2.02 second jump? Figure this. Ready, set, jump. Hit. Okay, is that a good jump?
Long jump.
Yeah, you're in the air. You're kind of thinking about a few things, right? You're like, hey, I wonder what my mom's doing right now. I think I want a hot dog for lunch. Maybe I'll have a yogurt. Okay, kind of fun. All right, so that's kind of the ins and outs of this problem. So what is the y-axis? That's the height in this equation as far as meters goes. You have to look what it is. So your y component is in meters. Your x component is time in seconds. Okay, so you're using your x and your y-axis to label these things. Okay, how should we choose the window? Well, we just chose it. We realized that we're not going to jump backwards in time. We're not going to go negative time. So that's where you change your window. Okay, so let's go to the next problem. Let's see where we're at. Where am I at right here? Let's see. No, that one, okay. All right, so this is what we were just doing. So let's figure this out. Go here, this over here. 2.02. What was his maximum height? 17 something?
17.5.
So you have those two intersections. This one down here, that's garbage. So this is seconds. This is meters. 1 meter is a little bit longer than a foot, or than a yard, right? A little longer than 3 feet.
Yeah.
So this guy's doing this. Oops, nope. Bad draw. That's what's taking place. Okay? And we knew that right here, just a smidge into not going, that's when this person decided to jump off this platform or whatever it is. How long will it take the diver to reach the water? Did I say 2.01 seconds?
You did say that.
Okay, cool. That's a good fall. That's a good jump. Okay, are you going to hurt yourself if there wasn't water below you? Yeah. Can I move on?
Yeah.
Do you guys have all these slides? Yeah. Okay, I just want to make sure I did things appropriately. All right. So the height and feet of a football that was thrown can be modeled by this equation.
I like this.
Okay? So negative 16c squared plus 32t plus 6. What was the initial vertical velocity of the thrown football? 32 feet per second. Okay? How do I know that? This is where V naught lives. Okay? From what height was the ball thrown?
6 feet.
6 feet. How do we know that? Because this is H naught, my initial height. How high will the ball be after a half a second? Oh, we'll find that out. When will the ball reach its maximum height? Well, we'll find that out. And what is the maximum height the ball will reach? Estimate when the ball will reach the ground. Well, I'll tell you exactly when it's going to reach the ground. Ready for the calculator?
Ready.
Here we go. It goes here, goes there. Click here. Y equals. Still with me?
Yes.
Clear that out. And we're going to go negative 16x squared. Oops, x squared. Plus 32t. 32x. So I'm replacing t with x because that's what the calculator has. Plus 6. Okay? We might want to hit zoom standard. So zoom 6. So when we graph it, it looks like that. Can I see the maximum height of the ball?
No.
No. So I'm going to have to adjust the window. Did I throw the ball into negative seconds?
No.
No. So I'm going to do this. I'm going to change my window. Maybe go negative 2 here. It looked like it went far enough out. I might have a little bit of negative on my y-axis. And then I'm going to change this to, I don't know, maybe 30 again.
You should do 27.
27. And if I hit graph, Can I see the whole parabola as far as the important stuff? I see where it crosses the x-axis, y-axis, the vertex. Still with me? Okay, where it crosses the y-axis is at 6. 1, 2, 3, 4, 5, 6, which is right there. What did that 6 represent? What did that 6 represent in our initial? Yeah, the height of the person that he threw the football, 6 feet. Okay? So the ball itself is actually 6 feet off the ground. So it's going to hit the ground right here. It's going to get to its maximum height here. I have time in seconds here. I have feet here. So we can figure out a lot of information. Does this, where it crosses the x-axis, mean anything? No, we're not traveling back in time. Okay, so let's figure out the items about this. Okay, so how do I find the vertex? Where do I go? We can go negative b over 2a, plug it in, do all that with arithmetic, or we can do this on the calculator. Second, what? Trace. I want to find, it's a parabola. I want to find a max or a min? Max. It was the highest point, right? So I'm going to find a max. I hit number 3. I'm going to use my arrows. Now I'm looking down here. This is where I'm at in 3, 2. Oh, here it comes. Am I on the left side of where that maximum would be?
Yeah.
Enter. Go to the right side. Am I on the right side of it?
Yes.
Enter. Hit enter one more time. So 1.55 seconds after that ball was released into the air, it got to a height of 17.24 feet. Okay? When did the ball hit the ground? I'm almost done. Second what? Trace. I want a 0.
2.
I want to be on the left side of it. I want to make sure I go to negative. Hit enter. Hit enter one more time. If you start seeing stuff like this, that means still 0. Negative 1 e to the negative 12. That means 1.0 times 10 to the negative 12, which is a bunch of zeros. So at 2.17 seconds after this person threw the ball, they launched it. Ladies and gentlemen, I want you to do me a favor. I want you to just try worksheet P. What does try mean?
Attempt.
Give it your best shot.
Give it your best shot. Do I understand that you're not pros at this yet?
Yeah, we'll get there.
We're going to have some fun. Get out of here, guys, girls. Have a great day. The 3 of you who missed the test, come